Welcome to the 13th chapter of the Crystal Clear Electronics, where we will be looking at DC motors. In the second video, our lead presenter is still Ambrus Zelei.
And my partner is Bence Bárány. We have a demonstration tool here. Please say a few words about it.
Yes, I brought down his engine model. I would like to show you how it works. It's a simple DC motor, and as we've discussed so far, there are magnets here, and if I stop it, it's more visible to see the coils. By the end of this video, we'll understand how it works.
Yeah, that sounds great. Indeed, our goal today is to understand everything here, the role of each component. In the first video, we explored the clear links between electrodynamics, that is, electromagnetism, and the forces created by magnetic fields. Using this, we now create a DC motor in our imagination, which we also call a direct current motor using the English term.
So far, two magnetic fields have emerged. According to Lorenz's law, when a current-carrying wire is placed in a magnetic field, a force is created on the wire. But the wire itself also generates a magnetic field, right?
Yes, if you want to build a motor, there must be a permanent magnetic field, and there must be a coil that creates the magnetic field that moves with it. Inside the DC motor, which is the simplest structure we're examining right now, there is a stationary magnetic field created by permanent magnets. We can also use the permanent magnet term abbreviated, which is PM. Imagine what happens if a loop with a current flowing through it is placed inside the magnetic field, as shown in the figure. Lorentz forces act on a section of the conductor and create torque, causing the loop to rotate. Here, we need to know that the torque changes the rotation of the bodies, or more precisely, their angular momentum. It's like accelerating the rotation of a carousel in a playground, changing its angular momentum. It is when we apply torque to the carousel. But we also use these tools from everyday life, an Allen key and a screwdriver. They are also used to apply torque. That's why I've just brought these to show you. Torque is usually calculated as force multiplied by a lever. So, for example, the force exerted by your finger and this lever is the lever of force. For this reason, the unit is the Newton meter, so force times lever. I think it's easy to remember. The Lorentz force also has a similar effect on the conductor loop, up to the point where the forces on the two branches of the conductor are aligned. Here in the drawing, they are placed one above the other. Because they are of equal magnitude but in opposite directions, they cancel each other out, and no torque is created. If we leave the leading loop in this position, it won't be able to start from here. However, if it spins anyway, there is a chance of getting it through this point, but the problem is that the forces would start to slow it down.
Ányos Jedlik, one of the greatest inventors of the 19th century, has also experienced this problem. He realized that if we change the direction of the current in such an arrangement just before the steady state happens, then the forces will change in a way that keeps the loop spinning.
If you think about it, you can see that by reversing the forces, the torque acts again in the right direction. So if you change the direction of the current after 180 degrees of rotation, you can achieve a constant rotational movement. It's performed by the so-called current transformer or commutator. There is one small problem. As the loop rotates, the torque decreases. Our theoretic machine wouldn't produce consistent rotation like this. It would jump after every half turn. If we place a second conductor perpendicular to the first loop, which is connected to our direct current source through the commutator at every quarter turn, the pulsation of the torque will be smaller. If we increase the number of loops, we'll get a relatively smooth rotation. The machine constructed by Ányos Jedlik in 1829 was the world's first operational electric motor, and it contained the three basic elements of a DC motor. The stationary part, called stator. It creates the stationary magnetic field with permanent magnets. The rotating part, called rotor, and the commutator, responsible for changing the direction of the current flowing in the rotor. This process is called commutation. The diagram shown here is illustrative of the commutator. So in this design, the battery would be short-circuited by the commutator turning.
Let's take a closer look at the main parts of DC motors.
The DC motor can be taken apart to three main parts: the stationary part, the rotating part, and the commutator, as you can see in the top right figure. Let's start with the stator. The stator is the part of our machine that is stationary. It does not move. It creates a stationary magnetic field. Until now, we have assumed that this part is made with permanent magnets, which contribute to the creation of the permanent magnetic field. However, in reality, in many DC motors, the stator is made with electromagnets that create the stationary magnetic field only when power is applied. It has the advantage that we can control the strength of the magnetic field. The ferromagnetic materials used in the stationary part shape the magnetic flux lines and provide mechanical strength and protection.
Our next main part is the rotor, also known as the armature.
The rotating part of the DC motor is typically made from ferromagnetic material. You can see it here. Copper conductors are wound in the grooves of the rotor. Again, iron has a role in concentrating the flux lines and making sure the conductors stay in place. The coils are connected to the commutator as shown in the figure.
And finally, a few words about the heart of the DC motor, the commutator, and the brushes that contact it.
The commutator is a cylinder mounted on the axle of the rotor on one end. The rotor consists of copper segments, which are isolated from each other. We will also take a closer look at this motor. Stationary brushes made of carbon or graphite are pushed against the commutator by springs, allowing current from the external DC voltage source to flow through the rotor. The disadvantage of this solution is that the brushes are subject to mechanical wear over time and need replacement, and the coal dust produced where the brushes contact the rotating axle can short-circuit the isolated segments of the commutator.
This suggests that there is more than just a brush solution.
Yes, but we will discuss this and how to control DC motors in our next video. For this video, thank you very much for your attention. Bence, thanks for your help.
If you feel you have understood everything from this video, move on to the third video in the DC Engines chapter. Bye!
Bye!